IoT sensors is a development application for visualization of sensor data. Some of the supported sensor types are temperature, pressure, humidity, air resistance, ambient light, accelerometer, impact, compass. It can also control the sensor, like trigger 2D or 3D calibration for a compass, toggle LEDs, display gravity, gyroscope, battery state of charge. The sensor data arrives as a label followed by JSON object with the data, and the label tells the application what kind of data is received. The communication is over BOE, TCP or UART. UART is only supported on macOS since iOS does not have UART support. Finally, the application can bridge TCP to BOE or TCP to UART, which means that when data is received from one interface, it is automatically forwarded to another. This can be achieved with any server that will forward data between clients like gRelay or GNCOM, where GNCOM also supports a UART, which is linked to the group of clients. More on that later. So let's start by running the application on iPhone. Once installed and started, it will ask the user to approve BOE connectivity in order to connect to sensors. Once this is approved, it will look for supported sensors. The default sensor name is Thingy91 UART, as shown here at the top. And if we go to the connectivity settings, you can see that the BOE name can be changed to match any name we wish. There is also the possibility to connect to IP and port. The recently used BOE devices are shown here. The application will also indicate devices that we have not connected but are in range and are supported. Then for IP, there is a list of recently used IP addresses and ports. At the bottom, there is a disconnect button and the bridge button. The bridge button bridges the two interfaces so that any data arrived from one of them is automatically forwarded to the other. Since we are already connected, we can close and start playing with our first sensor, which is Thingy91. Supported data are temperature, pressure, humidity, air resistance, ambient, infrared, red, green and blue, and a graphic for accelerometer. If we tilt the sensor, you can see that the graphic for accelerometer changes, and also the light changes. At the bottom, we have a lock with the communication. If we press the lock label, this is started or paused, and you can see that the communication is a label that describes what data follows, and then the JSON object with the actual data. We can clear the lock or start it again. Finally, we can toggle LEDs with the toggle switches. Thingy91 also has a built-in button which currently is configured to trigger the blue LED, and when I click this switch, the state of the LED and the screen changes to show the new state. Finally, we have a battery state of charge, by default in percent. If we tap that, it will change to voltage and back. Now let's show another sensor. We can change to this board, which is a self-driving robot, a very interesting project, which has a compass. And to visualize the data, let's create a bridge. So we will receive the data from the BOE and we will bridge it to this IP address and port. Then we are asked to approve connection to local devices. In our case, we are trying to connect to the laptop. Once approved, it will try to connect again, and you can see that we already have some data. Let's tell the device to send us compass data, and the display will change to show the compass data. If we rotate the car, you can see that the compass changes, and if we tilt, then the gravity changes. Now if we send the command to stop, no more data is received, but we can trigger compass data with the compass label or stop it. We can also hold, and there is another button called heading, which will ask the car to provide only heading data. This is again a compass with much less data sent over the Bluetooth link. At the bottom you can see that there is a nice trace of the heading, and if we change to compass with gravity, you can see that now we have a trace with the gravity as well. So now as I tilt the car, the trace will display the new data. Then we can hold the trace to examine it, or reset it and then enable the trace again to receive new data. Other options supported by the self-driving robot car are compass calibration. If we trigger it with the calibrate button, we are asked to rotate the car horizontally on a flat surface. As we do so, there is a progress indicator, and once it reaches the final, then the 2D part of the calibration is complete. By default, 3D calibration is used. This changes by pressing the 2D or 3D button before the calibrate. And now it asks us with X0 on a flat surface, rotate or tilt east-west. Let's go to the top, and here, apart from compass, you can also see data from the magnetometer. If we rotate it, so that x-axis is 0. Now we can start measuring the vertical field. Tilt the car, and once tilted enough, you can see that the bar is reduced. The goal is to reduce it as low as possible. Done. Now we have a label here that the minimum is measured, and if we rotate, okay, now it wants to reduce the angle. Done. And now if we tilt to the other side, we can measure the maximum. Anyway, that's for the calibration. The car is doing the whole thing, and this application pretty much tells the car to start calibration and interprets the data to help the user perform this part. The main goal is to visualize the compass data. We can cancel the calibration with the load button or erase the existing calibration with default. So let's load. Finally, if we point the car towards north, that's pretty much good enough. There is a button, mag, for magnetic heading. By default, we are using the true north, and you can see here heading 0.8. If we press mag, then we are changed to display the magnetic heading, which is about 5 degrees of difference. And if we press again, we are back to true north, and the difference is by the declination as shown here, 5.78 degrees. Now another option that we have is to receive data from the TCP connection. So for example, I will disconnect the car by pressing the connection status label. Now I will disable also bridge. Then again, I want to connect to this IP address and port without any BOE connectivity. And now the laptop will provide the same data. To achieve this, I can connect the Thingy 91 board, and another application on the laptop detected this connection and starts sending data to port 81 on localhost, so that we can examine it with the netcat terminal. And since we are already connected, we receive this data. Now you can see that the battery is green, charging. Finally, when a user does not have any supported sensors and maybe they want to develop their own and use this application to display them, let's clear the lock. According to the documentation provided here for IoT sensors, one can send commands like GPIO 0 equals state, set it to 1, and you can see that the LED changed to 1. If we press the same button, it changes to 0, and now the sensor received the command output 0 state 0. We can also send O at the same time. Let's say GPIO is 3F. Now all of the LEDs are turned on, and we can turn them off as well. Or let's say we want only one of them, or all of them turned off. Then let's say we want to send some data from accelerometer, and the accelerometer graphic is changed. So on for the others. We can simulate low battery states with battery or B. Let's say 3500. And now we have a red battery for depleted, or we can say, okay, let's put 4 volts. Finally, we can send compass, and you can see that when we receive compass, this is a different sensor than the one we are displaying right now, and the UI changes. Our message was compass with gravity, so we have compass indicator with gravity. If we omit the gravity, then we have only compass. Or we can say we want plain gravity, gyroscope, then some other interesting row sensors are for accelerometer, which is oh, I didn't copy it. Okay, so that's the accelerometer, and then magnetometer, and they are displayed on the same, pretty much the same screen. Oh, this is the wrong one. Okay, so these two sensors are supported together, and the outer layer is the compass. Inside we have the acceleration, and then there is some extra data related to calibration states and so on. That's it. Oh, and how did I set up the communication with TCP server? Very straightforward. Going to httpstorm.com, tools. Here are GNetcom and GRelay that I mentioned earlier. They are available for various operating systems. Going to Mac, we download the latest executable, and there is some description and YouTube video how to use this. Then once you run the application, there it is. Once you run the application, it accepts connections from clients. In our case, here is Netcat, and here is the iPhone application. And that's it.